Here we discuss Euler's theorem. In fact, it is a generalization of Fermat's little theorem. Fermat's little theorem, if you remember, it is if P is any prime number and A is any integer such that P does not divide A, then A raised to P minus 1 is congruent to 1 modulo P. This is actually Fermat's little theorem. Now, let us think of getting a number in the place of P minus 1, some Fm, such that A raised to Fm is congruent to 1 mod M for any integer M. Here this theorem is true for prime number only. Fermat's little theorem is true for prime number, and A is a number such that Pa equal to 1 or P does not divide A. Now suppose we have M any integer and A is an integer such that Am is equal to 1. Can we find an integer Fm such that A raised to Fm is congruent to 1 modulo M? So this is the basic fact in Euler's theorem. So before going to the theorem, let us have certain observations on taking some numbers like M equal to 4, M equal to 9, 12, etc. So let M equal to 4 first we take. Then our aim is to find such a number Fm such that A raised to Fm is congruent to 1 modulo M. When M equal to 4, the positive integers less than or equal to 4 and relatively prime to 4 are, that is, positive integers less than or equal to 4 and relatively prime to 4. Relatively prime to 4 are. We know by checking 1 and 3. You can see. Because 1 is such that 1, 4 is equal to 1. That GCD of 1 and 4 are 1. And similarly, GCD of 3 and 4 are also is 1. And therefore, 1 and 3 are relatively prime to 4. The only numbers less than or equal to 4. The numbers 1, 2, 3 are less than or equal to 4 and 4. Among these, 1 and 3 are relatively prime to 4. And this 1 and 3 has certain property. 1 square is congruent to 1 mod 4. 3 square is also congruent to 1 mod 4. So this 1 and 3 have the property that 1 square is congruent to 1 mod 4, 3 square is congruent to 1 mod. So we are getting a number here 2 that we are expecting in the place of Fm here. So this produces a number 2 here. Now let us take another number, say M is equal to 9. When M is equal to 9, the number of integers, positive integers, or the positive integers less than or equal to 9 and relatively prime to 9 are 1, 2, 4, 5, 7 and 8. These numbers are actually positive integers less than or equal to 9 and relatively prime to 9. And these numbers also have the property, you see. 1 square is clearly congruent to 1 mod 9. 2 square is congruent to here actually 1 raised to 6, let us say. 1 raised to 6 because there are 1, 2, 4, 5, 7, 8, such 8 numbers are here. So 1 raised to 6 is congruent to 1 mod 8. 2 raised to 6 is also congruent to 1 mod 9. 4 raised to 6 is congruent to 1 mod 9. 5 raised to 6 is congruent to 1 mod 9. 7 raised to 6 is congruent to 1 mod 9. And 8 raised to 6 is also congruent to 1 mod 9. All these you can verify very easily. So here also we are getting a number 6 such that in the place of that fm, a raised to fm congruent to 1 mod 9. So when m is equal to 9, we are getting a number 6 such that 1 raised to 6 is congruent to 1 mod 9. Similarly, up to 8 raised to 6 is congruent to 1 mod 9. And if you take any product, that is also raised to 6 is congruent to 1 mod 9, we can verify. And now let us take a third number. For example, m is equal to 12. The number of positive integers less than or equal to m and relatively prime to 12 are 1, 5, 7 and 11. These are the numbers which are less than or equal to 12 and relatively prime to 12. And there are such 4 numbers. So you take 1 raised to 4 congruent to 1 mod 12. You can see that 1 raised to 4 is congruent to 1 mod 12. And 5 raised to 4 is also congruent to 1 mod 12. 7 raised to 4 is congruent to 1 mod 12. 11 raised to 4 is also congruent to 1 mod 12. So this number m equal to 12 generates a number 4 here, satisfying then this property a raised to fm is congruent to 1 mod m. So when m is equal to 12, it generates a number 4. Now let us see what are these numbers. When m is equal to 4 we have taken, there we found a number 2 such that 1 square is congruent to 1 mod 4, 3 square is congruent to 1 mod 4, like that. So this 4 is producing a number 2. M equal to 9 produces a number 6 satisfying this property, and for m is equal to 12 there exists a number 4 which satisfies a raised to fm is congruent to 1 mod m. Now what are these actually? 2, 6, 4 corresponding to 4, 9 and 12, etc. And here we get a number called Euler's phi function. Now let us define what is Euler's phi function. It states like this: let m be a positive integer, then the Euler's phi function, which is actually denoted by phi of m, phi corresponding to m, phi of m, that is actually a number like the number that we got here, 264. So if m is a positive integer, the Euler's phi function phi of m is the number of positive integers less than or equal to m and relatively prime to m. So Euler's function phi m is the number of positive integers less than or equal to m and relatively prime to m. For example, here when we have taken m is equal to 4, we found phi of that 4 is 2. Phi of 4 is 2. The number of integers, positive integers less than or equal to 4 and relatively prime to 4 are 1 and 3. When m is equal to 9, the integers less than or equal to 9 and relatively prime to 9 are 1, 2, 4, 5, 7 and 8. There are such 6 numbers. So when m is equal to 9, phi of m is equal to 6. Phi of m is equal to 6. When m is equal to 12, the number of positive integers less than or equal to 12 and relatively prime to 12 are 1, 5, 7 and 11. So 4. So when m is equal to 12, phi of m is equal to 4. Now let us take another example. Compute phi 11. Phi 11. So here we have to determine the number of positive integers less than or equal to 11 and relatively prime to 11. We know 11 is a prime number. So all the numbers less than 11, 1, 2, 3, 4, etc., 9 and up to 10 are relatively prime to 11. So there are such 10 numbers here, and therefore phi of 11 is equal to 10. If p is a prime number, we can verify, we will show it later. Phi of p is actually p minus 1. That result we will write afterwards. Now compute phi of 18. Phi of 18. What are the number of positive integers less than or equal to 18 and relatively prime to 18? We can see that 1 is less than and relatively prime to 18. 1, 5, 7, 11, 13 and 17 are the numbers which are less than or equal to 18 and relatively prime to 18. We have to check all these numbers. 6 in between this 5 and 6 there is a number 6, but it is not relatively prime to 18, so it is not included here. So you have to find out the number of numbers, positive integers which are less than or equal to 18 and relatively prime to 18. So they are 1, 5, 7, 11, 13 and 17. So 1, 2, 3, 4, 5, 6 numbers are there. Therefore, phi of 18 is equal to 6. So phi of m, that function gives you the number of positive integers less than or equal to m and relatively prime to m. So to calculate phi of m, for the time being, we have to list all the positive integers less than or equal to m and relatively prime to m. And you count the number of positive integers, and that will be phi of that value. Now let us go to that result. Earlier I mentioned this. If here 11 is a prime number, phi of 11 we got 10, and if m is equal to 13, you can see that phi of m is equal to 12. So that is the result. So we write it as a lemma. A positive integer p is a prime if and only if phi of p is equal to p minus 1. So the Euler's function corresponding to the value p is p minus 1. Then p is a prime. If p is a prime, then phi of p is p minus 1. So let us try to prove this formally. So let p be a prime number. Then the positive integers less than or equal to p and relatively prime to p are 1, 2, 3, etc. up to p minus 1, and therefore there are such p minus 1 numbers less than or equal to p and relatively prime to p, and therefore phi of p is equal to p minus 1. Now conversely, assume that for any integer m, phi of m is equal to m minus 1. We have to prove this m is a prime number. Now phi of m, that is the number of positive integers less than or equal to m and relatively prime to m are, is actually m minus 1 we have taken. Now we have to prove m is a prime number. Suppose there is a factor for m, that is m is not a prime. Let m be not prime. In that case, there exists an integer d which divides m. D, where d is such that 1 less than or equal to d less than or equal to m minus 1. One of the factors of m will be in between 1 and m minus 1. So that divides m. Since d divides m, this dm is not equal to 1. That is, d and m are not relatively prime. So there is a number which is less than or equal to m minus 1, which is not relatively prime with m. And therefore, if you compute phi of m, which will definitely be less than m minus 1, not because there are such m possibility, m minus 1 possibility is there. This d can be one of these, one from 1 to 3 except p m minus 1. But dm is not equal to 1 means this d is not relatively prime with m, and therefore in the calculation of phi m will be that less than m minus 1. Phi of m is less than m minus 1, which is a contradiction. Because phi m is m minus 1, we have assumed. Here we are getting phi m is m minus 1. If there is a factor which divides, if there is an integer which divides m, then definitely phi of m will be less than m minus 1, which is a contradiction, and therefore m is a prime number. Therefore, m is prime. Hence, we have the result: a positive integer p is a prime if and only if phi of p is equal to p minus 1. Now, let us have certain observations. Earlier, while proving Fermat's little theorem, we used a fact that if p is a prime number and a is any integer such that p does not divide a, then the residues of these multiples of a, that is a, 2a, 3a, etc., p minus 1 into a is actually a rearrangement of 1, 2, etc., p minus 1 modulo p. That is the residues of the integers a, 2a, 3, etc., p minus 1 a modulo p are a permutation of 1, 2, 3, etc., p minus 1. That means the residues are 1, 2, 3, etc., p minus 1 in some order, that's all. A similar result we can prove here also. For that, let us take some number like, let m is equal to 12 and a is equal to 35. Now, the number of the positive integers less than or equal to m and relatively prime to 12 are here 1, 5, 7 and 11. 1, 5, 7 and 11 are the positive integers less than or equal to 12 and relatively prime to 12. So here let us observe a fact here. You see 1 into 35, if you calculate, similarly 5 into 35, 7 into 35 and 11 into 35, the residues of these numbers 1 into 35, 5 into 35, 7 into 35, 11 into 35 modulo 12 are 1, 5, 7, 11 in some order. Or in other words, 1 into 35 is clearly congruent to 11 mod 12. 5 into 35 is congruent to 7 mod 12. 7 into 35 is congruent to 5 mod 12. 5 mod 12. And 11 into 35 is congruent to 1 mod 12. So this is the observation that we are getting. So it shows that the residues of 1 into 35, 5 into 35, 7 into 35 and 11 into 35 modulo 12 are 1, 5, 7, 11 in some order. Now we are going to generalize this idea. That is the next lemma. Here 1, 5, 7, 11 are that of 12 are actually they are the numbers, positive integers less than or equal to 12 and relatively prime to 12. And A is an integer 35 such that AM equal to 1. AM equal to 1. They are relatively prime. So generalizing this idea, we get the result like this. Let M be a positive integer and A is any integer and A be any integer such that AM equal to 1. A and M are relatively prime. Let R1, R2, R3, etc. are phi M, because there are phi M, Euler number. Such a number of numbers are there relatively prime to M and less than or equal to M. So R1, R2, R3, etc. are phi M. Be the positive integers less than or equal to M and relatively prime to M. Then the least residues of the integers A R1, A R2, A R3, etc. A R phi M modulo M are a permutation, an arrangement or in some order, a permutation of R1, R2, R3, etc. Rn, R phi M. Just like we got here. We have taken M is equal to 12, A is equal to 35, AM is 1, relatively prime. Then the positive integers less than or equal to 12 and relatively prime to 12 are 1, 5, 7, 11. Here in this place R1, R2, R3, etc. are phi M. Then the residues of 1 into 35, that is AR1, 5 into 35, AR2, etc. 11 into 35, AR phi M are 1, 5, 7, 11. That is R1, R2, R3, etc. R phi M in some order. It's only a permutation of R1, R2, R3, etc. R phi M. So we prove this result first. First we will show for any I, ARI M, AR1, AR2, etc., AR phi M, M is equal to 1. That is, every ARI is relatively prime to M. Every ARI is relatively prime to M. ARI M is equal to 1. Suppose ARI M is not equal to 1. That means it is greater than 1. And let P be a prime factor of ARI M. That is, P divides ARI and also P divides M. P divides ARI and P divides M. Now P divides ARI means P divides A or P divides Ri or both. P divides A or P divides Ri. Now P divides Ri and P divides M means RIM is not equal to 1, which is a contradiction. Here R1, R2, R3, etc. R, phi m are relatively prime to m, and therefore RIM should be 1. But since P divides Ri and P divides m, Ri and P have a common factor P, therefore RIM is not equal to 1. So P divides Ri can be discarded. It is not the correct. Now take the case P divides A. If P divides A and here P divides M, this implies we are getting AM is not equal to 1. A and M are not relative. But in the hypothesis it is given that AM is equal to 1. So this is a contradiction. So ARIM is equal to 1. Every ARI, that is AR1, AR2, etc., AR phi m is relatively prime to M. The next thing we are going to prove is no ARI for any ij is congruent. That means if ARI is congruent to ARJ for any I comma j in between one and phi m, suppose ARI is congruent to ARJ for some ij in between 1 and phi m. Since congruent modulo m, we want to prove no ARI is congruent to ARJ for different ij modulo m. Suppose there exists ij such that ARI is congruent to ARJ modulo m. Then since AM is 1, A and M are relatively prime. By cancelling this factor, we get Ri is congruent to Rj mod M. Now Ri and Rj are actually residues of modulo M. That is the residues of the remainders less than or equal to M. So since Ri is congruent to Rj mod M and Ri and Rj are the least residues modulo M, this is possible only if Ri equal to Rj, because Ri is congruent to Rj mod M means M divides Ri minus Rj, and Ri and Rj are less than or equal to M, and this is possible only if Ri equal to Rj or Ri minus Rj equal to 0. So Ri congruent to Rj mod M only if Ri is equal to Rj. That means the least residues of AR1, AR2, etc. AR phi m are distinct, and they are actually R1, R2, etc. are phi m in some order. Hence the result. Now we are in a position to prove the Euler's theorem. The Euler's theorem states that let m be a positive integer and a is any integer such that am equal to 1, that is a and m are relatively prime, then a raised to phi m is congruent to 1 mod m, where phi m is the Euler phi function, Euler phi function, or simply Euler function. Proof. given phi m is the Euler function value for this m, that means there are phi m positive integers less than or equal to m and relatively prime to m. So let r1, r2, r3 etc. r phi m be the positive integers less than or equal to m and relatively prime to m. Then by the lemma that we discussed just now, if r1, r2, r3 etc. r phi m are positive integers less than or equal to m and relatively prime to m, then the least residues of ar1, ar2, ar3 etc. ar phi m is a permutation of r1, r2, r3 etc. r phi m. Then the least residues of ar1, ar2 etc. ar phi m are r1, r2, r3 etc. r phi m in some order. And therefore ar1 into ar2 into etc. ar phi m is congruent to r1, r2 etc. r phi m modulo m. Here there are such phi m numbers here, product. So it is a raised to phi m into r1, r2 etc. r phi m congruent to r1, r2 etc. r phi m modulo m. Since every r1, r2 etc. r phi m are relatively prime to m, r1, r2 etc. into r3 etc. r phi m is relatively prime to m is 1. So since r1, r2 etc. r phi m is 1, we can divide this by r1, r2 etc. r phi m. We get a raised to phi m is congruent to 1 mod m. Here we use AC congruent to BC mod m, and with the Cm equal to 1 we have A congruent to B mod m. Thus we have the result A raised to phi m is congruent to 1 mod m. That is Euler's theorem. So if m is a positive integer and A is any integer relatively prime to m, then A raised to phi m is congruent to 1 mod m. Let us take some examples. Let m equal to 24 and A is any integer relatively prime to m. Then the positive integers less than or equal to 24 and relatively prime to 24 are 1, 5, 7, 11, 13, 17, 19 and 23. These are the positive integers less than or equal to 24 and relatively prime to 24. They are actually 1, 2, 3, 4, 5, 6, 7, 8. That is phi of 24 is equal to 8 here. So by Euler's theorem we have A raised to phi m is congruent to 1 mod m. That is A raised to A, you take any A raised to phi m, phi 24, A raised to 8 is congruent to 1 mod 24. In particular, Suppose you take A is equal to some number 77. Clearly 77 is such that 77, 24 GCD is 1, or 77 and 24 are relatively prime, and therefore 77 raised to 8 is congruent to 1 mod 24. 1 mod 24. Even otherwise also you can verify this 77 raised to 8 is congruent to 1 mod 24, because 77 is actually congruent to 5 mod 24. So 77 raised to 8 is congruent to 5 raised to 8 mod 24, and 5 raised to 8, you can see that 5 square is congruent to 1 mod 24, and therefore 5 raised to 8 is congruent to 1 raised to 4 mod 24, that is congruent to 1 mod 24. So this 5 raised to 8 is congruent to 1 mod 24. So directly by using the property of congruence relation, you can verify that 77 raised to 8 is congruent to 1 mod 24. So even otherwise, by using Euler's theorem, we can see that 77 raised to 8 is congruent to 1 mod 24. So as we use the Fermat's theorem for finding the remainder, when a number of the form a raised to n divided by a number, another number, here also we can find the remainder by using Euler's theorem. So let us take such an example. Find the remainder when 245 raised to 1040 is divided by 18. What is the remainder when 245 raised to 1040 is divided by 18? Here 245 is clearly congruent to 11 mod 18, and therefore 245 raised to 1040 is congruent to 11 raised to 1040 mod 18. This 11 is a number such that it is relatively prime to 18. 11 and 18 are relatively prime, and therefore by Euler's theorem, we are using Euler's theorem here, 11 raised to 5 of 18 is congruent to 1 mod 18. Now what is 5 of 18? To compute 5 of 18, you have to identify all the positive integers less than or equal to 18 and relatively prime to 18. You can see that there are such 6 numbers. 1, 2 is not there, 3, 4 not there, 5 is there, then 6, 7 is there, then 9, 10, 11 is there, then 13, then 17. So 2, 4, 6. These are the numbers relatively prime to 18 and less than or equal to 18. And therefore 5 raised to 18, 518 is actually 6. So 11 raised to 6 is congruent to 1 mod 18. Now we want to reduce this 11 raised to 1040 mod 18. We have 11 raised to 6 is congruent to 1 mod 18. So try to write 1040 in terms of 6 by using division algorithm. we have 1040 you can write as 6 into 173 plus 2, and therefore 11 raised to 1040 you can write as 11 raised to 6 into 173 plus 2, which you can write as 11 raised to 6 raised to 173 into 11 square, and 11 raised to 6 is congruent to 1 mod 18, so it is congruent to 1 mod 18, so 1 into 11 square mod 18, and this is actually congruent to 13 mod 18. 11 square 121, if you find, you can see that we leaves the remainder 13, so this congruent to 13 mod 18. Hence 245 raised to 1040 is congruent to 11 raised to 1040 mod 18 is congruent to 13 mod 18. Hence the remainder is 30. Remainder is equal to 30. I told you Fermat's little theorem is a special case of Euler's theorem, and therefore Fermat's little theorem can be derived from Euler's theorem. You know, Fermat's little theorem states that if P is a prime number and A is an integer such that P does not divide A, or A and P are relatively prime, then A raised to P minus 1 is congruent to 1 mod P. So here we are using the situation of Euler's theorem. Here P is a number such that AP equal to 1, or A and P are relatively prime, and phi P is, since P is a prime number, phi P is P minus 1, and therefore by Euler's theorem A raised to phi m is congruent to 1 mod m. So here A raised to P minus 1, phi P is P minus 1 is congruent to 1 mod P. 1 mod P. So Fermat's little theorem is a special case of Euler's theorem. Also, by Euler's theorem we have, if m is any integer such that am equal to 1, then A raised to phi m is congruent to 1 mod m. So from this you can write as A into A raised to phi m minus 1 is congruent to 1 mod m. By remembering the inverse of a modulo m, if A be congruent to 1 mod m, we say B is the inverse of A modulo m. So here A is A raised to phi m, since we can write as A into A raised to phi m minus 1, we can see that A raised to phi m minus 1 is the inverse modulo m of A inverse. A raised to phi m minus 1 is the inverse modulo m of A. So to find the inverse modulo also, we can use Euler's theorem. A raised to phi m minus 1 is the inverse modulo A, inverse modulo m of A. And another application of this Euler's theorem, this is one of the application. And the second application is to solve a linear congruence. Suppose we have a linear congruence Ax congruent to B mod m with the Am equal to 1. That is, A and M are relatively prime. Then since Ax congruent to 1 mod M is solvable because A has got an inverse in the form A raised to phi m minus 1, we can multiply Ax congruent to B mod m by the inverse of A modulo m, which is A raised to phi m minus 1. So A into A raised to phi m minus 1 is congruent to A raised to phi m minus 1 into B mod m. From this we get the solution into X. Multiplying this by A raised to phi m minus 1. That is, X is congruent to A raised to phi m minus 1 into B mod m. So linear congruence can also be solved by using Euler's formula, Euler's theorem, by multiplying by A raised to phi m minus 1. So solution to Ax congruent to B mod m is A raised to phi m minus 1b, residue of A raised to phi m minus 1b modulo m. For example, let us try to solve the congruence 35x congruent to 47 mod 24. Here 35x congruent to 47 mod 24 can be simplified because 35x you can write as 24x plus 11x. So it is 11x congruent to 47 mod 24, and 11 and 24 are such that 11 24 is equal to 1, and therefore the solution is got by multiplying by 11 raised to phi of 24 minus 1. So X is congruent to phi A raised to 11 raised to phi m, that is phi 24 minus 1 into 47 mod 24. So we need to calculate phi of 24. So 11 raised to phi 24, here as earlier we found X is A raised to phi m minus 1 into B mod m is the solution. So 11 raised to phi of 24 minus 1 into mod into 47 mod 24 is the solution. And you calculate phi of 24 minus 1, we know phi of 24, you can see that it is 7. So it is congruent to 11 raised to phi of 24 is 8. 8 minus 1 into 47 mod 24, that is congruent to 11 raised to 7 into 47, you can write as minus 1 mod 24 because 48 is a multiple of 24. And this 11 raised to 7 into minus 1 mod 24 can be reduced to 13 mod 24. Hence, the solution to 35x congruent to 47 mod 24 is the residue of 13 mod 24. Now there is another application of this Euler's theorem, which is theorem due to Cauchy. We call it Cauchy theorem. The theorem says this: let m1, m2, etc. mk be any positive integers and A is any integer such that AMI equal to 1 for all 1 less than or equal to I less than or equal to k. Then A raised to LCM of phi m1, phi m2, etc. phi mk is congruent to 1 mod LCM of m1, m2, etc. mk. Proof is just a direct application of Euler's theorem. Since for every I, AMI equal to 1, by Euler's theorem we have A raised to phi mi is congruent to 1 mod mi. For all I, one less than or equal to I less than or equal to k. Let L equal to LCM of phi m1, phi m2, etc. phi mk. Then L divided by phi mi for any I is an integer. And therefore A raised to phi mi raised to L by phi mi is congruent to 1 mod mi. 1 raised to L by phi mi is 1 for any 1 I less than or equal to k. That is, A raised to phi mi raised to L by phi mi means A raised to L is congruent to 1 mod mi for all I such that 1 less than or equal to I less than or equal to k. And therefore A raised to L is congruent to 1 mod LCM of m1, m2, etc. mk. We have this result earlier. A raised to L is congruent to 1 mod m1, m2, etc. mk. Hence, A raised to L. L is LCM of phi m1, phi m2, etc. phi mk is congruent to 1 mod LCM of m1, m2, etc. mk. Also, there is a corollary to this theorem. If this m1, m2, mk, etc. are pairwise relatively prime, then the LCM of m1, m2, etc. mk will be the product m1 into m2, etc. mk. So, in that case, m1, m2, etc. mk are pairwise relatively prime, then LCM of m1, m2, etc. mk will be m1 into m2, etc. mk product. and therefore the above result reduced to a raised to phi m1, phi m2, etc. phi mk. LCM of this is congruent to 1 mod m1 into m2 into etc. mk. That is the result that is derived from this Cauchy's theorem. Now let us try to do some problems from exercise part. First problem is this: compute phi of 21. So in order to compute phi of 21, you have to write down all the positive integers less than or equal to 21 and relatively prime to 21. Clearly 1 is such a number, 2 is relative to prime to 21, 3 is not, 4 is relatively prime to 21, 5 is relatively prime to 21, 6 is not, 7 is not, 8 is not, 9 is not, 10 is relatively prime to 21, 11, 12 is not, because 12 and 21 have 3 factor 3, then 13, 14 is not relatively prime to 21, 15 is not relative, 16 is relatively prime to 21, 17 is relatively prime to 21, not 18, 19 is there, 20 is there. So 1, 2, 4, 5, 10, 11, 13, 16, 17, 19, 20 are the numbers relatively prime to 21. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Therefore phi of 21 is 11. Another problem is verify Euler's theorem. For each modulus, for modulus 10, for modulus 10, or for m is equal to 10. So given m is 10, then the number of positive integers less than or equal to 10 and relatively prime to 10 are 1, 3, 7 and 9. 1, 3, 7, 9 are the numbers relatively prime to 10. And therefore phi of m, that is phi of 10 is equal to 4. Therefore by Euler's theorem, a raised to phi m is congruent to 1 mod m for any integer a relatively prime to m, where a is a number such that am is equal to 1. So a raised to phi m, 4, is congruent to 1 mod 10. 1 mod 10. Now by taking some a relatively prime to m, we can calculate. For example, 9 and m 10 are such that 9m is equal 9 10 is equal to 1, and therefore 9 raised to 4 is congruent to 1 mod 10. Next problem is find the remainder. Find the remainder when 7 raised to 1020 is divided by 15. What is the remainder when 7 raised to 1020 divided by 15? We know 7 square is congruent to 4 mod 15. Therefore, 7 raised to 1020, since it is equal to 7 square raised to 510, is congruent to 4 raised to 510 mod 15. Here 4 and 15 are such that 415 is equal to 1, and therefore by Euler's theorem we have 4 raised to 5 of 15 is congruent to 1 mod 15. So we have to compute what is 5 of 15 to calculate 5 of 15. The positive integers less than or equal to 15 and relatively prime to 15 are 1, 2, 4, 7, 8, 11 and 13. Therefore, 5 of 15 is equal to 1, 2, 3, 4, 5, 6, 7. Hence, 4 raised to 7 is congruent to 1 mod 15. So, we have to reduce this 4 raised to 15 mod 15 by using 4 raised to 7 is congruent to 1 mod 15. So, write 510 as 7 into 72 plus 6 by division algorithm, and therefore this is congruent to 4 raised to 7 into 72 plus 6 mod 15, which is congruent to 4 raised to 7 raised to 72 into 4 raised to 6 mod 15. By this result, 4 raised to 7 raised to 26 is congruent to 1 mod 15. So 1 into 4 raised to 6 mod 15. And we know 4 square is congruent to 1 mod 15. Therefore, 4 raised to 6 is congruent to 1 cube mod 15. That is congruent to 1 mod 50. So, it is congruent to 1 mod 50. Hence, the remainder 7 raised to 1020 on division by 15, you get 1. So, the remainder is equal to 1. Now, the last problem that we do in this section is solving. Another problem is solving a linear congruence. Say, for example, 7x congruent to 8 mod 10 by using Euler's theorem. By the result we have, if we have a congruence relation A is congruent to B mod M, then the solution is given by x is congruent to a raised to phi m minus 1 into b mod m, because a raised to phi m minus 1 is the inverse of A modulo M. So X is congruent to A raised to 5M, 510 minus 1 into B, 8 modulo 10, using that result. So here we have to compute phi of 10. To compute phi of 10. The numbers relatively prime to 10 are 1, 3, 4, 5, 6, 7, then 9. So phi of 10 is equal to 4. So X is congruent to A raised to, so here A is actually 7. A is 7 here. So 7 raised to 4 minus 1 into 8 mod 10. That is congruent to 7 cube into 8 mod 10. 7 square is congruent to 9 mod 10. Therefore 7 cube is congruent to 63 mod 10. That is congruent to 3 mod 10. Therefore 3 into 8 is congruent to, so 7 cube is congruent to 3 mod 10. So it is congruent to 3 into 8 mod 10. Again it is congruent to, this is 24 mod 10 is congruent to 4 mod 10. Hence the solution is the residue modulo 4 modulo 10. The residue 4 modulo 10 is the solution to our linear congruence given 7x congruent to 8 mod 10. So with this I conclude this session. Thank you.